Alright, we're going to begin section 15.7 in this video, which is Stokes Theorem. So just first to kind of orient ourselves, let's go back to and talk about Green's theorem again. So recall Green's theorem relates a double integral over a planar region R to a line integral over the oriented curve C, that is the boundary of R. So remember, we're working in two dimensions when we're working with Green's theorem. So say we have some region R in the XY plane. Then that region R has an inherent boundary curve. And we just orient that boundary curve in the counterclockwise direction. And so Green's theorem tells us for the vector field f of xy equals m comma n, the line integral over this boundary curve C f dot dr is equal to the double integral over the region R of the partial of n with respect to x minus the partial of m with respect to y. So Stokes theorem does a similar thing, and actually Green's theorem is a special case of Stokes theorem. So first I'm just going to kind of give an explanation of Stokes theorem that mimics this, and then I'll give what the actual statement is of Stokes theorem. But it makes it easier to remember the theorems if you actually kind of understand how they're relating a boundary to a surface, or a double integral in this scenario. And then Stokes theorem, you're relating a boundary, a line integral to a surface integral. So Stokes theorem relates a surface integral over an oriented surface S to a line integral over the oriented space curve C, that is the boundary of S. So let's just sketch a picture of basically it's doing the same thing we're doing it in Green's theorem, but now we can do it in a more general sense because we're doing it in 3 dimensions instead of being stuck in the XY plane. So let me sketch my surface first. And we're just going to sketch a very easy surface because I don't want my coordinate axes to interfere. So we'll sketch our surface and sketch our coordinate axes behind. And put some little to indicate we have a surface there. So now we know how to do a surface integral over this surface S. Given we're doing a surface, we need to have a surface integral of a vector function. We need to have an orientation to this surface. So we'll say that's the unit normal vector. So we'll say that we were given, for instance, upward orientation. Now, so we have an oriented surface. Now we want to relate that to a line integral of an oriented space curve. Then we have to use whatever orientation is given to this curve by the orientation of the surface. So remember, the way we do that is with our person that's walking along the boundary curve. Their head has to point in the same direction as the normal vector. And then as they walk around the boundary curve, the surface needs to remain to their left at all times. So for this example, this will be the induced orientation of the boundary curve. It will go in that direction. So now what does Stokes theorem actually say? What is the relationship between some surface integral here and a line integral on that boundary curve C? And actually on our other picture, we should have labeled our curve C as well. So go back up to our Green's theorem picture and label that C. So now we're doing the similar thing. So we're doing the same thing that we were doing in the Green's theorem, but now we're doing it in 3 dimensions. So Green's theorem is just a scenario like this where you just happen to be in the XY plane. So Green's theorem is just a special case of Stokes theorem. So now what does Stokes theorem actually say? Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation let F be a vector field whose components have continuous partial derivatives on a space that contains S except possibly on the boundary of S. Then the line integral over C of F dot dr is equal to the surface integral over S of the curl of F dotted with unit normal vector n ds. So what it's given us is we could evaluate this line integral directly because we know how to do line integrals, or what we can do is we can evaluate the surface integral of now your vector field. The surface integral you're going to evaluate here is not just going to be of your vector field. It's going to be of the curl of F. That's going to be the new vector field for which you're going to evaluate the surface integral. So please be careful of that you're not just doing F dotted with n ds. You're doing curl of F. So your first order of business when you're using Stokes theorem, when you're going to evaluate the surface integral, will be to find the curl so you don't accidentally try to use that vector whereas you should be using this vector. So while we're introducing the theorem, let's introduce something that you will use quite regularly. So the we've already seen it, but there's a shortcut formula for if we use our favorite parameterization. So as usual, for our favorite parameterization, x equals x, y equals y, z equals f of x, y. Page 1042, equation 6. For Stokes theorem becomes, so it's the same equation that we were using before when we were doing the surface integral. So I'm going to rewrite this right hand side right there. So the surface integral over S of the curl of F dot n ds. Now remember, this is us parameterizing our surface. It has nothing to do with whatever our vector field was. So if we're able to parameterize the surface, regardless of, because this equation 6 is actually in section 15.6. It's not in 15.7. But that equation works if you're using this parameterization and you're doing a surface integral of a vector field, then you can still use the formula which says that this is equal to the double integral over the region R of negative m times f sub x minus n times f sub y plus p dA. But you have to be careful here that when you're using this for in terms of Stokes theorem, this m, n, and p are not from F. The m, n, and p are from curl of F. So you have to take your curl first. That's why I said make sure you take your curl first when you're doing a Stokes theorem problem, so that you can kind of abandon that vector field f and make sure that you're using the curl of f. That should be your vector field that you're using throughout the problem. So where caution, f is not equal to MNP, but instead curl of f is equal to MNP. So the formula works exactly the same, just make sure you're using the correct vector field. You should be using the components of the curl of f, not the components of f when you do that. Then arguably probably the most important formula for using Stokes theorem is that the surface integral over surface S1 of the curl of f dot then a normal vector to the surface, we'll call it N1. Oops, that was supposed to be right there. The curl of f dot N1 ds. According to Stokes theorem, if we have this surface integral and we need to evaluate that surface integral over this surface S, it's the same as the line integral over the boundary curve C, which C is a boundary curve for S1 of f dot dr. But Stokes theorem also tells us that if we have a line integral over some boundary curve C of f, then that is equal to, according to Stokes theorem again, the surface integral over some surface S2 for which C is the boundary curve of curl of f dot N2 ds. So what this says is that you have a boundary curve. It doesn't matter what surface you use. If as long as that boundary curve is a boundary for that surface and 50 other surfaces, doesn't matter. As long as they share that boundary curve, you can evaluate whichever one of these integrals is easiest for you to evaluate. So if we have some messy surface over here, well, Stokes theorem allows us to take that messy surface and change it to a line integral. Now we have to be evaluating this integral over that messy surface, not just any old surface integral. But if this surface is difficult to evaluate that integral, then Stokes theorem says, well, we can evaluate this line integral. And then if we see that boundary curve for this surface is also the boundary curve for whatever this surface is, which is much easier to work with, then instead of evaluating this, we can switch to this easier surface and evaluate that one. So you do whatever is the easiest. So you'll see me use this quite regularly. And then a good number of the questions in the textbook are flat out telling you to change your surface from what they give you to some other surface and then evaluate this line integral this surface integral instead of doing that surface integral that they originally gave you. All right, so let's look at an example. So we are on page 1054. We're going to start with number 3. All right, so the directions say in exercise 1 through 5, use Stokes theorem to compute the line integral over C of f dot dr, where C is the curve that bounds sigma, and that has the induced orientation from sigma. So keep in mind, if your directions say use Stokes theorem to evaluate the line integral, then that means you have to do the surface integral instead. Otherwise, you're just up to you to just choose whichever one you want to do. If you're given a problem that's a line integral and you could use Stokes theorem and you want to switch, you can, or you can just directly do the line integral. But if they give us the line integral and they tell us we have to use Stokes theorem, then we have to do the surface integral. All right, so this problem, they give us our vector function is f equals y negative x z, and they tell us sigma, or I'm going to use s, is composed of the part of the cylinder x squared plus y squared equals 1 between the planes z equals 0 and z equals 1, and the part of the plane z equals 1 inside the cylinder x squared plus y squared equals 1. N is directed away from the z-axis on the cylinder and upward on the plane. All right, so what I'll do is I'll write down what the surfaces are, but then from there I'll sketch just so we have a good idea of what's happening here. So we have two surfaces here. We have S1, and that is the cylinder x squared plus y squared equals 1, and z is between 0 and 1. And then we also have the top of the cylinder, I think, between z equals 1. Yes, and then we have the top of the cylinder, so S2 is just z equals 1, and then that's inside of the cylinder, so x squared plus y squared is less than or equal to 1. So now what we're asked to do is evaluate this line integral. Now we could, if our hand wasn't being forced, we could go through and find what the boundary curve C is, and then just parameterize that and evaluate this directly. But we don't have that option because they said we have to use Stokes theorem, which means they want us instead to evaluate the surface integral over these two surfaces, and we're going to have to add them together. So the surface integral over S1 of curl of f dot n ds plus the surface integral over S2 of curl of f. So this normal vectors for that surface, so we need an n1 there, plus curl of f dot n2 ds. All right, so that's what they want us to do. So now a couple of things. One, let's go ahead and find the curl of f, and also I'm going to sketch what we have here so we can kind of get an idea of how this actually relates to our discussion of Stokes theorem. So let's just start with the sketch first, and then we'll compute the curl after that. So our cylinder and at the bottom, let's put a dotted line at the bottom down here because the cylinder's open at the bottom and it is closed at the top. So that's our surface right there. Now, what we were told is that the normal vector is directed outward on the cylinder, and that was S1, so this is N1, and directed upward on the plane, I think, directed away from the z-axis on the cylinder and upward on the plane. Yes, okay, so on the plane, this was N2. So that's the surface that we have there. It's just a combination of these two surfaces. So we need to evaluate both of these surface integrals and add them together. So now what we also could do is use the last thing that I gave you all, which was that once we have the surface, now what we can do is look at the boundary curve. Now the boundary curve on that surface, the plane, and the boundary curve on the cylinder are actually different. So these boundary curves for those two are different. But what we can do is just look at the entire thing. The cylinder with the plane is one unified surface, and then that dotted line down there at the bottom becomes the boundary curve. So if this is our entire surface, the boundary curve really is that little circle right there in the XY plane. So what we can do now is we can say, well, we had this surface here, but let's instead just work with a surface S. We're going to make that surface S. This thing. Now, yes, it's in the XY plane, so normally we would sketch that in 2 dimensions, but I'm doing it down here so we can just actually see that you take your surface that they give you, and if there's an easier surface that has the same boundary curve, then you use that easier surface instead. So now we need to look at the orientation for this normal vector right here to see what orientation that would give on that curve down there at the bottom. And then we need to make sure that this has that exact same orientation that this does. All right, so now this normal vector, the surface that corresponds, and we did a problem like this in a previous lecture, the surface that corresponds to that normal vector is actually the cylinder. So now if we're going to look at this curve down here, that means our stick figure's head needs to point in the direction of that normal vector. And as the stick figure walks around this curve, this cylinder needs to remain to his or her left at all times. And in order to do that, that curve down there would be oriented in that direction, which says that this curve right here should be oriented in that direction as well. And now with that, if we can also look at, if we have a curve oriented in this direction, what is the normal vector on this surface right here? And that normal vector, the stick figure's head would have to point that way if the surface to remain to his or her left. So now we're just going to call this one N, and this is going to be our new surface, and we're just going to call it S, because we can use this surface instead of having to deal with that surface at all. And now we don't have to worry about parameterizing the cylinder and parameterizing the plane. We just use that plane and we're done. So our problem now has been reduced from parameterizing the cylinder, parameterizing that plane, setting this up and evaluating, and adding, to parameterizing that plane right there, which is very easy, finding that normal vector, and then setting up our integral. So now, instead of using this, we now have the line integral over C of f dot dr equals the surface integral over S, where this is S now, of the curl of f dot n ds. Now, I told you all in the previous lecture that we rarely ever use this notation for evaluation purposes. It's normally purely a notational thing, but when you have a plane, you actually can use this. I mean, you can use it in other scenarios as well. It's just very easy to use it with the plane. Other scenarios, it's not very easy to use that setup. So that means instead of having to do a cross product of magnitude and cross product, you can just look directly at your plane and say, okay, what's my normal vector? What's the normal vector of that plane? Put it in right there. It has to be unit normal vector though, of course, because this specifies this is a unit normal vector. So that's why I had to, once I oriented this curve, I had to specify what that is, which direction that vector points. So now let's go back up to our picture. What is this vector? The unit normal vector that points in that direction. That would just be 0, 0, 1. Oops, sorry. 0, 0, 1. Now we still need the curl of f, so that's the other thing that we're missing. So the curl of f equals, we have, what was our vector field? Our vector field was y, negative x, z, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And here we are going to get 0, 1, 0, so we'll get 0 there. We'll get 0 there as well. And we're going to get negative 1 minus 1. So we'll get negative 2. So this is our M and P. So this is M, that's N, and that's P for our usual setup. Then now usually we would take, and this is why I said we don't tend to use this. So I'm going to reiterate this again. So we also would have to find for a parameterization of our surface. So I'm pointing at the wrong thing. I should be pointing at this picture right here. So for a parameterization of our surface, which we don't need to do this, but I'm going to write it down anyway. The way we would parameterize this is because this is just a plane z equals 0. We would parameterize that as x equals x, y equals y, z equals 0. So our f of x, y would be equal to 0. So our plane, our surface S is x equals x, y equals y, z equals 0. And the bounds of x and y are that x squared plus y squared is, was our radius 1, or did I make that up? Yes, x squared plus y squared is less than or equal to 1. So if we were to parameterize our surface, that's how we would do that. And then we have our favorite parameterization. So this setup would be done for us entirely. I'm not going to go through that way. That's where we would have negative m times f sub x and minus n times f sub y plus p times 1. So if we were to set this up that way, that's how we would do that using this parameterization. But the reason I'm writing this down is so that we can see that if you were to do yourself r sub x cross r sub y for this parameterization, you will get this exact same vector 0, 0, 1 that we have up here. So that doesn't tend to usually be the case. Normally your parameterization would give you something different than what you might just naturally look at as your normal vector. So that's why I said we don't tend to use this in practice, because oftentimes whatever you may think of as a unit normal vector won't be in line with the parameterization that you have. So in this scenario, it will work out that if you were to do r sub x cross r sub y, you would get that same vector n. So I'll write that down on the next page, which is why we're able to just use our intuition in this problem instead of actually doing that cross product. Now, we wouldn't do the cross product anyway because we're using our favorite parameterization. It's already done for us. But r sub x cross r sub y, now I'm assuming I'm doing this in the Korea, would actually end up in this scenario being equal to 0, 0, 1, which is just so happens to be what we chose when we looked. I mean, we didn't really have any option with that plane, but usually you would have different things that you can end up encountering. Or what happens is that your parameterization doesn't match this normal vector, and then you remember you have to plug your parameterization into your function, your vector function. So I lost our vector function. We had 0, 0, negative 2 now. So for us, this ends up being, I'll rewrite what I had on the last page, the surface integral over S of curl of F dot N ds. So in practice, we would take our parameterization, plug it into this thing, do r sub x cross r sub y, and then to do the dot product of those two things. And that's how we would go evaluate our integral here, just because of the simplicity of this problem. This doesn't tend to be the case in general. We end up with the double integral over region R of, we had 0, 0, negative 2. So that's with our parameterization plugged in there, because all these were constants. So we do still have to plug in x equals x, y equals y, z equals 0 into here, but all of those were constants, so there's nothing to do there. Then dot it with r sub x cross r sub y, which we were just able to establish what that was by inspection. So 0, 0, 1 dA, which is equal to the double integral over r of -2 dA, but that's the same as -2 times the double integral over r of 1 dA, which is just -2 times the area of r. And our region R was just a unit circle in the xy plane. So this is just going to be pi r squared, pi times 1 squared. So we would just end up with -2 pi is our answer there. All right, so now I did this by not going through those steps. So what I recommend that you try now is doing this a couple of different ways. One of which is that so try this using the double integral over r of -m f sub x minus n times f sub y plus 1 dA. So using our shortcut formula, it will be the exact same as what we did here, but just so that you can understand why what I did this way is a legitimate approach, where I just did the normal vector by inspection. And then you can also go through just the basic approach where even with you set this up entirely on your own. So that means that you take your parameterization, you plug it in there, you compute r sub x cross r sub y, you take the dot product yourself, you'll see that you still get that exact same thing, or this exact same thing, regardless of which approach you use. But again, I reiterate, in general, you would not want to just find your normal vector by inspection, because whatever you find may not match whatever parameterization that you're using to plug into m, n, and p. And then that's going to, what ends up happening is that your integral ends up being off by a constant, whatever the magnitude was of the normal vector that you found. All right, so I'll stop this video here and then we'll continue section 15.7 in the next video.